Today we're going to go over how to compare our point cloud data to design. So we're going to touch on how to model our objects in AutoCAD, how to compare that point cloud to those objects and colorize it based on the distance. We'll go over all the possible deliverables that we can get from that, whether it's colorizing the point cloud, picking key areas of interest and highlighting how far the as-built is out from design at those locations. We're going to show you how to render and visualize the point cloud. We're going to show you how to bring an animation into your PDF and have it available to the client at the click of a button, and how to go into Civil 3D and cut section planes of your model and your point cloud and visualize that as well. This video is very long, but there is a lot of detail in here and a lot of information. So if you stick it out, you may learn something. And if you have anything you'd like to share in the comments where I can learn something too, that would be fantastic. So in order to compare our scan data to design, I will need design data to compare to. So what I have open here is a typical design CAD drawing of a construction site that I have some data that we can compare to. So this is a drawing that I built up coming off of engineering drawings, and it's just built off of line work, polylines, 3D polylines, and this was used to lay out features in the field and to compare our as-built data to. So I can't do much with just line work. So I'm going to want to turn all these simple polylines into 3D solids or 3D meshes. So to do that, there's a few different ways to do it. I can either use the extrude command and select a line, hit enter, and extrude to wherever I see fit, whether that's another line or by distance. So this will come in on the layer I had current. So I can either match it to the layer of the line work. So I can either match it to the layer of the line work or set that line work current before doing the process. So again, that's extrude, grab my object, enter, snap it to the next line. So you'll notice this line is destroyed in the extrusion process. That one is maintained, but I lost my top line. So that's something to keep in mind if you don't want to lose that line work. But of course, you can just copy and paste into another drawing that you wish to do all your modeling from. Another option is the press pull command that will take a bounded area and extrude it. So this retained the polyline on the top, and of course with the press pull command you can bring out the faces if you want, pull them in and do your tweaking that way. You can also say if I want to use the extrude command, you can do multiple objects at once, which can be handy. And another feature that I like to use is for more complex objects like this containment area here, is I'll create a surface for the top of concrete, which is the red line work here, create a surface from the bottom of concrete, create a volume surface from those two surfaces, and extract a solid from that surface and snap it up in place where it should be. So that's a nice little technique for more complex objects. Once we're finished modeling our design drawing, we're going to end up with something like this. Typically for pipe networks, I usually like to draw out either the top of pipe, center of pipe, bottom of pipe, whatever is supplied to us in the design drawings, create a circle at one end and use the sweep command to draw the pipe. And then you can use the shell command to create the inner wall of the pipe. The issue that you can see right here is when we have a 3D solid, the face resolution is quite low. And unfortunately, when I bring this 3D solid into the software we're going to use later to compare it to our as-built, that poor face resolution is going to show up. So there's a couple things we can do to mitigate this. I'm just going to create let me just change my viewport. So I'm looking at left, come over to view, set my left viewport. Let's jump onto an empty layer. And I'm just going to create a circle at the center of this pipe. Snap it to a quadrant. Okay, so that circle denotes the exterior of pipe, and you can see there's a massive deviation between what actually will be exported and where it should be. So what I can do is I can turn this into a mesh. So I'm going to come over to my mesh tab and click the little drop down arrow to look at our tessellation options. So for mesh type and tolerance, I'm either going to use mostly quads or triangle. And I'm going to uncheck this meshing primitive solids checkbox. So if it's checked, it's going to fit in a primitive cylinder. The only issue with that is it's going to round off the top and bottom edges. It will round it off less so as I increase these two values here. But instead of just to get rid of that issue, I'm not going to mesh a primitive solid. I'm just going to create a mesh from the 3D solid that represents a cylinder. So these are the settings I'm going to use. You can copy them if you'd like. And then I'll go over to smooth object. Click my 3D solid, and I'm going to create a mesh. So you can see now the face count significantly increased. There's still a little bit of a gap here. So to check how much, I'm going to go to the midpoint of this face. And let's turn off polar snapping. And jump over to nearest. And let's see how bad it is. So 1/10 of a mil and 1 mil. So it's a mil out. For what we're doing, that's perfectly acceptable. I'm not measuring up to a millimeter. I'm not going to worry too much about a millimeter. If I did want to get that down, I do have the option of creating a mesh cylinder and modeling this in a completely different way. The way I do it's much quicker versus creating a mesh at every single bend. So it's really up to you. You can bring this into other software packages, increase the amount of faces too. That's a perfectly viable other option. So once we're happy with this, I'm going to go ahead and save this, and we'll jump into Navisworks next so we can export an FBX. So let's pull that up. I'll just mention quickly that Civil 3D used to be able to export FBXs in previous versions. So if you are working with an older version of Civil 3D, you can try and use the FBX out command. I think they discontinued it in 2016, but I'm not 100% sure on that. So once I have Navisworks open, I'm going to append my drawing. Okay, so I have my drawing in Navisworks now. The pipe networks will still, oh no, you can start to see the segmentation I was talking about here. So these are two pipes that I didn't bother to remesh, just because I know I'm not going to do any comparisons to them. But if I were, I would go back and turn all of my pipes into meshes. So this is the one I did, and you can see it's looking a lot better. So I have everything into Navisworks, and in here all I'm doing is outputting an FBX, so it's quick and easy. If we had textures, lights, or cameras set up, we could do that. Here we don't. We're not worrying about that at all right now, and it's out of the scope of this tutorial. We're going to want to export as a binary format. It's going to save us some space on our design model, and we will not require an ASCII format for what we're doing. So go ahead and export that. Title it something that will make sense to you. And that's it. We're done with Navisworks. So once we're done in Navisworks, we're going to go ahead and open up CloudCompare, and we're going to bring that FBX in. So it's as simple as dragging or dropping or using the open tool in the top left corner of the screen. And it's important to remember we have to note our global shift values here, because when we bring our point cloud in, we're going to want to make sure we're applying the same global shift. That design model I had was geo-referenced based on the engineering drawings. And of course, our scan data is also going to be geo-referenced in the same coordinate system. In this case, it's actually a site-based ground coordinate system. Not that that matters too much. So for this example, both the X and the Y are ending in values of 300. You're going to select yes to all. That will apply that global shift to the entire data set. And now you have your FBX file in a CloudCompare. If you'd like to, it's all broken up into different entities in the DB tree on the left here. If you want to select one, you can just click it on the screen and it will bring you over to that entity in the DB tree, at which point you can turn it on or off or do any type of manipulation or analysis you would like on that particular entity. For example, you could click on that, turn off the wall, and view the design data inside. So now we are going to pull in our point cloud of this same site that I collected back in January. So you can see here that the global shift is actually different. So I'm going to want to go ahead and make sure it is the same, otherwise it will not line up. So I just added 300 to the X and Y. Okay, so now our point cloud data is in here. You can tell, it might not be obvious to you, but it is landing in the right place. So I can turn off my, let's actually increase that point size. Okay, so I can turn on and off my design to kind of do a quick comparison and verify that yes, in fact, it is in the right place. You can see all the walls are lining up, and for example, it's covered up now, but there is a bunch of pipes underground here, and you can actually see that you can see the face of that pipe is showing up in the point cloud there. For today's exercise, we're going to be looking at this middle containment area over here. So we could just bring our point cloud into Autodesk Recap, convert it to an RCP, bring it into Civil 3D, and create a surface from that, and create a surface or we already have a design surface of top of concrete, and do a volume surface from those two surfaces and use elevation banding to create a heat map. The only problem with that is that compares Z values between two surfaces that are directly above each other. So that's fine for this area in here where it's pretty much flat and we only want to compare the difference in the Z value. But in areas like this where there's some significant sloping going on, using that method will compare the difference in distance directly along the Z axis, which isn't actually really what we want. We want to compare the difference in the two surfaces perpendicular to the surfaces. So that's what the method I'm about to show you is going to do. And also for vertical walls, say if this structure was built, we obviously could not bring that into Civil 3D without some manipulation of the data to flip the as-built data 90 degrees so that this would be facing up. And that's the only way we could really compare that into AutoCAD. So the method I'm about to show you is pretty handy because it solves that issue. So to make our data a bit more manageable, I'm just going to turn off the model. I'm going to cut out this center section because that's what we're wanting to compare. So I'm hitting T for the snip tool, and I'll just be rough with this and cut out the area of interest, and it's I to select in and enter to complete the command. And I'll turn off the rest of the points. So this is what we want to compare. Just to clean it up quickly, I'll run a quick CSF filter on it. That seems okay. Okay, so that stripped off most of the outlying points. I don't need those anymore. You could go and clean this up a lot more, but that's not really the purpose of this exercise. And I may just quickly chop out some points here. And delete to delete those. Okay, I'm not going to spend too much time because I'm just trying to show the concept of what we're doing here. You should note there is some snow on here and some dirt, and these pedestals are obviously still showing. So if I was actually doing this, I'd probably take some more care to clean up this point cloud, but I can still filter that out, which I'll show you how to do in a bit. Okay, so we have the point cloud we're going to work with. Now we want to grab the model. So these are all broken up into different pieces. So I'm going to want to, just to make life easier, I'm going to want to grab all these and merge them into one. So I'm just holding control right now and picking on all the 3D models that I want to bring in and compare to each other. Or sorry, compared to the point clouds. So I have those selected. It's edit and merge, and that's going to create a new model with those merge points. Turn that off. Okay. And just to do a bit of housekeeping, going to get rid of that. I'm going to keep that for now. And just to clean this up, T for my segmentation tool, and inside, and delete to delete everything outside. Okay, so the area I'm really interested in is these side slopes here and the main containment area. Okay, so let's bring back my point cloud. It's looking good. So now what we're going to want to do is select our point cloud and select our model, holding control so we have both. Then we're going to come over here and do a compute cloud to mesh distance. So what that's doing is it's computing the distance between the point cloud and the mesh along the normal. That is to say, perpendicular to the point, to the surface that the points create, to put it simply. So you have a few options in here. These are your approximate distance. So these are some statistics you can look at to get an idea of what you're dealing with. So you can see there's some points that are 2.4 meters away, and that's just this data down here where the model ends, but the points keep going. And we can flip our normals, which will, and where we're showing a negative value now, it will flip that to positive, and that will just depend on how you want to display your data. And our max distance, so I know that this surface, this as-built, isn't going to be more than, say, 20 centimeters out. So I can set that for now, and that will just help me get rid of a lot of points right off the bat. I'm going to click compute, and I'm done. So I'm really pretty much done with this merged or mesh, and I can just start to work on these, on this new scalar field of the point cloud. So if I come down to my display ranges, I'm just going to tweak that and cut that back right now. So I'm just getting rid, I'm going to take that out, move that over, move this over. This will give me an idea of what is actually out and what is just points on here I don't trust that are actually ground. So obviously you can see it's the first thing it's showing is the bottom of all these pedestals. There's that dirt there. There's that bit of snow there that I remember. And I don't know if that is snow or not, so I'll jump back to RGB. Let's crank the point size. Yeah, there's definitely some snow on there. Yeah, the concrete's obviously not doing that. So that's fine. Jump back to the scalar field. And I'm going to do a bit of cleaning on this. So I'm pulling over my slider for displayed points. Normally I wouldn't have to do this too much because I would have spent the time to clean the cloud. So I'd say that's fair, that's all true data that we're showing now. And to get rid of the points that are currently hidden, it's edit, scalar field, and filter by value. And we're going to export a new point cloud based on just those values. I can get rid of that old one. So now I just have the values that I was showing before. So you can still see like all this red stuff. It's probably erroneous, but I'm not like that. I'm sure is not concrete, but this could actually be where the concrete doesn't fit within design. So we're just going to leave that for now, and it won't really change anything too much. Okay, so I could turn on my histogram. This is a deliverable by itself now. So this is showing, this is basically creating a heat map of where the as-built surface isn't meeting design by the amount displayed in this histogram on the right. A quick note, if you want to alter your histogram decimal values or how it's displayed, just come over to display settings, and it's all in here. Yeah, that would be, let's see, it's not labels. Yes, display number of precision and other options. So that's one deliverable right here. And if we wanted to get rid of this, or I should say export this into, say, a Civil 3D plot, we would come down to tools. Sorry, it's display, render to file. Figure out where you would like to render it to. And you have the option of a JPEG or a bitmap, PNG, etc. I'm going to use a JPEG. Let's go. And you have a bunch of options here. So the zoom level is going to increase your resolution by a factor of this value here. It's obviously the higher resolution, the larger the image is going to be in terms of megabytes. So I'll leave it up to you to figure out what you want to, how much you want to zoom. I generally use something around 7. Let's give that a shot and see how it looks. Okay, so you can see here that the points have shrunk quite a bit, as has the scale bar value here. So what is going on? Let's take a closer look at this. So this check mark right here is telling CloudCompare to not scale features. So the point size, line thicknesses, all this text here. So we actually want to scale these features along with our zoom. So we're zooming in and we're going to scale those points back up to how we're actually seeing them. So let's try that again. Our text is back to the proper size. But it's still a bit small. The points are still on the small side. So I'm going to crank up my point size. So to get it back to looking like what I'm seeing here, I would want to match my point size with my zoom value. So if I set that to 7 and render to file, don't scale, okay. Okay, it's telling me it's done. So that's looking a lot better there. And this should theoretically look the same as that. So pretty close. Might be a slightly different. So you can play with your settings there. If that's still too big for you and you would like your points to look smaller, like there's some overlap, that's not too bad. That's about where I'd want it. Yeah. You can go ahead and manipulate your point cloud in as many different ways as you'd like. And continue to render those images and use them as you'd see fit. You can also create an animation that you can share with your clients through either sending them the raw output or hyperlinking a button on your AutoCAD plot that links to that animation in YouTube, or sorry, on YouTube, which I like to do. So let's go ahead and I'm going to switch my view to perspective to give a more realistic representation of what it would look like. You can also do this when you're taking your renders as well. So that's what it looks like under perspective, and that will give you a better idea if I was hovering here and looking at the point cloud. CloudCompare defaults to orthographic, which is much handier when you're clipping stuff. So to create an animation, you can use the quick command Control V to create a viewport and repeat that process as you orbit around your point cloud. So I have all my viewports. If you'd like to see where a viewport is going to be viewing, just highlight it and click apply. That will bring you to that view. So once you think you have all the viewports you'd like, set your visualization as you would want it to be displayed in the animation. I just want to bump my point size up a bit. Let's try 3. So I'm going to highlight the top one, hold down Shift, highlight the bottom one, go to Plugins and Animation. So let's try a 40-second animation here. You can increase your bitrate quite a bit. We're going to do 30 FPS, super resolution, and let's crank up the factor to 4. We'll just call it animation 1. Or animation, maybe orbit. And let's give that a shot and see how it turns out. Okay, let's see how that turned out. So that's looking pretty good. It gives your client a true three-dimensional view of how this point cloud looks versus a motionless render. It could just be an extra depth that they might appreciate, and they can see it from all angles, where when it's just a render, they're limited to what you chose to render to. So yeah, I'm happy with that. And you can get kind of fancy with it too. Like, we have the rest of the point cloud data already loaded into CloudCompare along with our model. So I'll see what I can do to try and get a little fancy with it, and I'll be back and see what we can do. I'll probably bring the raw clips into a video editing software to stitch it all together. But of course, just the way that is, you can bring that MP4 into YouTube and run it just that way if you'd like as well. So we also have the option of picking some discrete points of areas we would like to highlight to our client that would require further investigation. You can set your start index to whatever you'd like. That will change the point label. And this could just be useful if there's one or two or a few more particular areas you want to highlight to your client, saying, hey, these are out by this much and they are at this location. So we are going to want to show our global coordinates, and we'll save that as a label name XYZ. Just call it point list. And we do want to apply our global shift. Let's look and see what we have in that CSV. So we have our coordinates and our labels, but we don't have the values of the scalar field available to us. So there is a workaround there. We can also save it as a new cloud, and we should be done with that. And we would want to render this again to be able to graphically show where these points are. So I'll quickly do that. Let's turn that off. And so this is our new point cloud, which contains those points. And to get our scalar field back into that, we're going to want to rerun our cloud to mesh distance with that new cloud. So we have the new cloud selected, we have our merged mesh selected, run the mesh to cloud distance tool again, compute, okay, we're good. So now this point cloud has that scalar field built in, and you can see we're showing 48 mils up to 68 mils in those particular points, and then just save that point cloud as a CSV. We're going to want to show our column title, comma separated. Okay, so let's open up that CSV, and we'll open up our original CSV. And we'll just move some columns around here. So this is actually our northing because it comes in X, Y, Z. Let's grab that. So we have, let's get our point numbers in there. 400. And we want our signed distances. And you can see they do come in the same order when we save our point cloud. Everything lines up. So we're done with this. Sorry, we're done with this one. All we needed from here was our sign distances. And we're going to save this and use it later in our AutoCAD plot. So we're about done in CloudCompare, but the problem, we want to now bring this point cloud into Civil 3D. Let's turn that off. So we want to bring this cloud into Civil 3D to retain our colorization in Civil 3D. We're going to want to save our scalar field as RGB values. So to do that, we want to come over to Edit, Scalar Fields, and Convert to RGB. We don't want to mix it. And now you can see whether we're on scalar field or RGB, we have the same colorization, which will give us a point cloud in Civil 3D that is colorized based on our delta distances. So you can go ahead and save this now as an LAS. I'd like to touch on cloud to cloud comparison briefly. So I have the same data set. I've cut out a square and I'm going to compare it to the same area but at a different epoch. They're a few months apart. So what we're looking at now was captured in November, and this was captured in January, the following January, a few months later. So you can see the January data set has a stockpile here. It has some junk on the yard there. And the November data set, let me actually just increase that point size, has a car here and no stockpile there and a bit of snow right there. So to run the cloud to cloud comparison, we select the two clouds, and it's this button right here, cloud to cloud distance, and your selection order matters. So for example, say if we select the November cloud first and then the January cloud. Sorry, this is actually supposed to be 23. So if we click the November cloud first and then the January cloud, holding Control and run the process, you'll see the compared surface is the first cloud that we select. In this case, the November cloud. So the reference cloud is not having the tool being applied to it. It's simply the compared cloud that we're operating this distance to, or this cloud to cloud distance tool on. So if that, we can also swap if we want to, but for now, let's run the process on the November cloud. We press OK. So again, we can set our max distance. We can split our X, Y, and Z components. I never really used that. We can set our octree level. I just let CloudCompare do its job and pick it for us. But if I come over to local modeling, so if I don't select a model, it uses a nearest neighbor method to select the 2 points, which isn't the 2 points to which it's going to compare to, which isn't necessarily ideal. For most applications, we're going to want to use quadratic. You can use 2.5D if you have sharp edges. Say if you had 2 scans of a building, this might be the better option to use. But obviously we don't here, so we're going to use quadratic, and we have the choice of selecting how many points we want to use to make up our local model, or the radius of a sphere. So I'll just use points for this particular example. If I had some big gaps in the data, or say there is, yeah, I guess that's probably the best example. If there's some big gaps in one of the clouds, I could set the radius of my sphere larger than that gap, just to kind of mitigate that issue. And we're going to want to click compute. So we're done with that. And we did the process on the November cloud. So let's look at that. And we have our scalar field highlighted. Let's bring up our histogram. So one thing you're going to notice right off the bat is they're only absolute values. We're not getting a negative and positive. So this is strictly, this would be 2.48 meters from that other cloud, whether it's above or below. It's just going to give us absolute values here. And everything else applies that we went over. You can alter the visualization. You can remove points if you'd like. Everything else is the same. Where this might be useful is, say you're doing a monitor. There's a lot of actually places where it'd be useful. If you're monitoring a hillside and you have an accurate scanner, and you wanted to compare your 2 scans, it would be very useful. If you have some hydrographic data of a riverbed that's gone through some erosion and deposition, that would be another example. But the possibilities are really endless. So I just wanted to briefly touch on this. Besides the fact that I can only get absolute values, everything else is the same. Okay, so if you really want signed distances, which makes a lot of sense, I can see the value in that, there is a workaround to get that. So if you remember, with a mesh, we can get our signed distances, that is positive or negative distances. So the obvious answer here is just create a mesh. So I'm going to grab our reference cloud, the January 1st cloud, come up to edit, normals, computer normals, quadratic, and hit it with some sunlight. Okay, so we have our point cloud with normals, and now we're going to go to plugins, Poisson Recon. I don't really know how to pronounce that, to be honest. Octree depth, sure, we'll use 12. Make sure you outport density as a scalar factor. Okay. Okay, so we have our mesh now. I'll turn off the cloud. And again, we are going to add some color to that, or some light, I should say. Okay, so this is what it looks like with our scalar field, and we can cut back all the extra stuff that was created that we don't need. And we've seen this before. It's edit, scalar fields, and filter by value and export. Okay, so let's get rid of our old mesh. We have our mesh of our surface, and it looks pretty good. So now it's pretty straightforward. Let's delete that cloud. We don't need it. We have our mesh. We have our cloud. And let's do a mesh to cloud distance. Okay, so now you can see we have the signed distances available to us. Local modeling we don't, because it's computing our distance along the normal of the point cloud. And let's compute. Okay, so turn off our mesh. We have our point cloud. Now let's look at our scalar field. So you can see now we do have our signed distances. And again, you can adjust your visualization as you see fit. Yeah, if it's not the direction you want to display it, right now it's showing that the car, so everything above the reference surface is a negative value, and everything below the reference surface is a positive value. It's simple to swap that. You just flip your normals when you're doing your cloud to mesh distance. We're in Civil 3D now in our design drawing. We have our line work, we have our 3D solid that denotes our design in here. We'll go ahead and insert our point cloud that we just saved. Okay, looks like it's landing in the right spot. We'll go ahead and pick our point cloud, and we are going to cut some section planes here. So that you'll find in the top toolbar under the section tab, and we'll start off with a left section plane. And we can click that again and get some details on it. So we can choose to cut a plane or a slice. So we're going to want to do a slice because we want cross sections. We can define the width of our slice here. I'm going to do 30 centimeters. And we can define the location here. So let's start at 11380. That would be the easting of that point, or sorry, that line. Okay, and if we click on this little drop down here, we can set some additional settings. So the one we're going to concentrate on is this offset distance increment. So that number is how much that cross section will move every time I hit these arrows. So I'm jumping at 5 meter intervals right now. So when we end up plotting this, however, whatever distance you want to use for your cross sections, you can set it there, and then it's just clicking the arrow to move that cross section. It'll make a bit more sense once I jump into the side view. To turn the cross section on and off, we can click this live section button. And this cross section is actually cutting the model and the point cloud at once. So I'll go to our paper space and show you exactly what I mean. Okay, so I set up this paper space to show a plan view and a cross section view. And they will obviously automatically update with each other. So if I hop in here, this is the 11380 plan view or cross section. So I'll set that appropriately. You can see here that your points are displayed and the design model is displayed. So a few things to note. You're going to want this set in realistic as a realistic visual style. And you're going to want to add a transparency to your 3D solid. That will allow you to see through like this. And you can also adjust the size of your points by selecting the point cloud, and it's just up here. So set that to whatever makes sense for you. So I think that point size might be okay. So what I've done here is I've added some annotations just to help the client quickly see how far particular spots are off from design. And I've done that for all the cross sections that I'm showing. Theoretically, it doesn't really need that because it is colorized. So right here, you can see it's 42 mils off. It's this orangey red color. If I went up to the bar and look at the orangey red color, I'm looking at around 42 mils. So they aren't absolutely necessary, but it's up to you if you want to add them or not. Yeah, so once you set up one paper space like this, unfortunately we can only show one cross section at a time. So to repeat the process, you would copy the paper space, edit your easting value if you're going west to east, and click on your section view, and then just jump it up by one of the increments. So now we're at 11385. That's what I have denoted there, and the annotations I already made should line up, which again, you don't really need. So as a double check, I'm looking at a point that's green with a splash of yellow. So yeah, it's right around there, 6 mils. It jumps up on this bench here, and you can add as many cross sections as you like. Just to illustrate exactly how the animation button works, as long as your client is connected to the internet, they simply just click the button and they're automatically brought to the animation, which you can host on your YouTube channel and keep it unlisted. So just in case your client has any issue with their data being available publicly online. And the final deliverable we're going to be looking at is, of course, the point cloud viewer. So I dropped the as built into the point cloud viewer. We can visualize it with the rest of the epochs. That was in January. We have August. We have March. We have November, whichever one we want. So what this would do is we would send the link to the client. They could pull their own measurements. By this time, they're familiar with what color is representing the deviation amount. They can pull as many locations as they want and export these as a CSV. They can cut cross sections. So say if they really wanted a cross section right there, they can cut their own cross sections and do their own analysis. Again, it will be colorized to visualize exactly where it's out and by how much. So this is kind of really the Cadillac of visualization and exports, although I might be a bit biased here. But it really puts the power into the client's hands in terms of them extracting exactly the data they want. They don't have to come back and say, hey, what about at this location? How much was it out here? Now they have that capability themselves. So that wraps up the video. So these are just a few examples of how you can display your point cloud data, and that's compared to design or other point clouds. If you have any suggestions on anything I've missed or you're doing anything differently, please leave a comment below. I'm always eager to learn some new tips and tricks. So this is just what I do, and I thought I would share it, and hopefully we can get some discussion going and maybe all learn something.